Okay, so let's get started. It's 11 o'clock. Welcome, everyone. My name is Semih Salihoglu from University of Portland. I'll be chairing this session, the second tutorial on PODS on parallel query processing. Our speaker is Dan Suchu from University of Washington. So Dan is a professor at University of Washington, and he's a very prolific database researcher. Over the last 2 decades, he's done very significant contribution to many fields of databases, most notably known for his work in XML and probabilistic databases, on which he has 2 books, written 2 books, but also on other topics, including parallel query processing, on which he'll speak today, and data pricing, and other topics as well. So he's has many awards, which I won't list, but that list includes 2 Test of Time awards from PODS. And the last thing, he asked me to keep the introduction brief. The last thing that I'll just say is that over the last 11 years, 4 of his students, PhD students, has won either Sigmod Best Dissertation Award or were runner-up. So, 4 theses out of last 11 years were recognized as the best of the entire database community, or the second best. So that says a lot about the depth of the work that Dan has been doing. So with that, I'll leave it to Dan. There's just one thing, Dan. So the tutorial is 1 hour, 15 minutes. Dan will take questions in the middle, and probably if you have time at the end. Just the only thing we ask is, because the session is being live streamed, just wait for the microphone before you ask your question. And we have a volunteer, Swale, who will be bringing the mic around. Okay, so with that, I'll leave it to Dan.
Thanks, Semih. I hope the microphone works. Does it work? Okay. Okay, so I think I'm all set. No, I'm not all set. No, I'm all set. Let me just start by mentioning that this tutorial, I decided to base it entirely on some work that we have been doing at the University of Washington in collaboration with Paul Beam and Paris Coutris. Essentially, most of this part made it into Paris's thesis. And it is based on, the tutorial is based on the 4 papers that are listed here. The problem we are going to discuss is the following. We have data distributed on P servers that can communicate over a network, and we need to compute a query. And the question is, how much communication, how much data do we need to exchange in order to compute the query in parallel on these P servers? This model is called in the systems community the shared nothing parallel database model, in contrast with the shared memory parallel database model. So the shared nothing is the most scalable model, because the idea is that if you need to process larger data sets, or you need more performance, then you just add up more of these community servers, you rent more from Amazon Web Services, and your data can grow, or your queries will run faster. This model underlines many of the modern data analytics systems, and also underlines the first shared nothing database architecture, the Gamma machine, developed by DeWitt at Wisconsin in the mid-80s. So in order to analyze queries theoretically on this model, we need to raise the microphone. Can you hear me now better? Yeah, this is much better. What I'm going to do next, I'm going to briefly describe an abstraction of this shared nothing architecture, which is a variant of the bulk synchronous processing model introduced by Variant in the early 90s. It's a variant in the sense that we simplified it, and we called it the massively parallel communication model. So we have P servers, and we have an input data of size M. And think of M as being terabytes, think of B as being thousands or tens of thousands. That's the kind of scale. And initially, the data is uniformly partitioned on the P servers. Each server has like M by P tuples. So the computation proceeds in rounds. The servers, they exchange the data. Usually the entire data is being exchanged, sometimes even more. And then they compute, and then they can continue. They exchange data again and compute, and so on. An algorithm consists of several rounds. And the assumption here is, unlike the BSP model, the assumption is that the servers are infinitely powerful. They can compute anything you want, any undecidable problem, not to mention NP-complete problems. They can compute anything you want. The only cost, there are two cost parameters. One is the what we call the load, which is the maximum amount of data that any server receives during one round, and the total number of rounds. This is the only cost. This is what we are trying to minimize in this model. So in order to give you some intuition about how to think about this model, you might think first, why can't I do the following? In the first round, just send the entire data to server number 1. And since server number 1 is infinitely powerful, it can compute anything we want, and we are done. The problem with that is that now the load is M. That server will receive the entire data, and the load is much higher than the M by P amount of load that we expect from a uniform distribution. So now you say, aha, if I only can send M by P amounts of tuples to a server, let me repeat this for P rounds. And I'm going to send the data in chunks of size M by P to the first server, and after P rounds, it has collected the entire data, it can output anything we want. So we don't want this either. We would like the number of rounds to stay small. Ideally, we would like to have a single round, exchange just the data once, and then the query can be processed locally, and the load is only M by P, and the number of rounds is M. That is the ideal setting. As I will show you in this tutorial, this is not always possible. In practice, we need some constant number of rounds, and the load is slightly bit larger than M by P. It's M by P to some exponent, which is less than 1. If the exponent were 0, then we are back to the naive approach number 1. Okay, so this is the topic of my talk, some notations. We have studied only full conjunctive queries, and this is a limitation. We do not know the answers to the questions I'm going to address for Boolean queries or even for queries that have projections. So a full conjunctive query is a conjunctive query where all the variables occur in the head. Nothing is projected out. And I'm going to use blue for the query size. And in this tutorial, I'm interested only in the data complexity. The size of the input data is denoted in red. So every relation, every input relation, S1, S2, has a size M1 tuples, M2 tuples. These represent the sizes of the input relations. Sometimes I'd like to talk about the domain, the active domain, and then I'm going to use N for the size of the active domain. And the number of servers is P. And we are interested in the load, which is a function of the input data and the number of servers, also the number of rounds, actually. And it's a function that depends on the query. Okay, so this is a setting that we're studying. So why do we care about a good load? Because in parallel database systems, we care about speed up and scale up. Speed up is informally defined as the increase that you're observing in the processing speed as you add more servers. So tomorrow you want to answer the queries 10 times faster. Can you just rent 10 times more servers and run the query 10 times faster? Now, if your load is M by P, which is the ideal, and assuming that your servers are infinitely powerful, then you can assume, then you can observe a linear speed up. But in practice, a load will be more like M by P to some exponent, which is less than 1, and then the speed up is sublinear. So this is something to look into. We want to optimize the speed up. Any questions so far about the model? Okay, good. I always get I always manage to confuse people about the model, so I'm happy I didn't confuse anyone yet. So here is the outline of my talk. I'm going to start discussing this problem for the simplest queries. I'm going to spend most time here where we are going to assume that all relations have the same input size, the same size, and that the data is not skewed. And I'll explain what I mean by this. And for the first bullet, I'm actually going to dig a little bit deeper and show some proofs. Actually, one proof that will take 9 slides. I think it's important to see the beauty of how the theory can explain and inform what people do in the real systems. And that is my purpose of that proof, to show you the techniques that are needed to analyze this model. Then we are going to move to unequal inputs, something that database systems already do today, and we are going to understand the theoretical explanation for what they are doing and what they are not doing and should be doing. Then I'm going to discuss Q. I'm going to have very little to say about multiple rounds because Bas Gessman, who sits here, will have a talk in the afternoon, in the evening actually, about new results on the multiple round model that are much more relevant than what I can tell you about previous work. And then if we have time, I have 5 open problems that I'd like to share with you. Okay, so there will be proofs throughout this tutorial. I think they are nice proofs, interesting proofs, but just in case you're not looking forward to proofs, I have some highlights, one simple nugget from each of these 4 parts of the tutorials, and I'm going to explain what these nuggets are. So if you don't take anything away from this tutorial, take away those nuggets. Okay, basic query processing, and I'm going to start with join. We have 2 relations, R and S, and we want to compute the join, and there is no projection. So we want to join on the attribute Y. In this part of the tutorial, I'm going to assume that all input relations have the same size. So this is M tuples. And the standard approach in shared nothing architectures is to use hash-based partitioning. Throughout this tutorial, all the algorithms that we're going to discuss are based on hash-based partitioning. And this is the state of the art in systems. If you came Monday to a talk in the afternoon, Yufei Tao and KE, they have a new technique for parallel query processing that's based on sorting, and I'm not going to address that in this tutorial. Interestingly, this systems only use hash-based partitioning. So how does hash-based partitioning work? It's very simple. Every server that holds a fragment of the input data will iterate over its fragment and will send every record to a different server based on computing a hash function on the join attribute. So every server sends a record rxy to a server that is a hash function on y, and of course taken modulo p. And we do the same thing for S. And it's easy to see that after this single communication step, the servers can compute the local join, and we are done. We have computed the join. What is the load of this algorithm? The way to analyze it is to assume that the hash function is drawn from a set of universal hash functions. It's uniformly drawn from a set of universal hash functions. And with high probability, over the random choices of this hash function, the load per server will be M by P. However, there is a big caveat. It's going to be M by P only if the data has no skew. And what I mean by this is that no value of the Y column occurs too many times to skew, to overload one of the servers. How many times can we tolerate a data value to occur in R before we observe before we exceed that expected load of M by P? And in this tutorial, I'm going to keep it very simple. I'm going to say that if every data value occurs less than M by P times, then the data is without skew. And if a data value occurs more than n by p times, we call it a heavy hitter, and then we say that the data has skew. And this hides lots of things, including a detailed analysis using Chernoff bounds on what exactly happens, especially at that border between light hitters and heavy hitters, and it also obscures other things. But I'm going to simplify in this talk, and this is my definition of skew. So this is how systems work today. They use hash-based partitioning. Interestingly, they have a second technique, which is called broadcast join. So in broadcast join, they take advantage of the fact that often one of the relations is much, much smaller than the others. And then they keep R, for example, distributed as it came from the input. And if S is much smaller, they just broadcast a copy of S to every single server. And then they compute the join locally. Of course, that load will be as big as the size of S. It is only good, both theoretically and practically, it's only good if the relation S is much smaller than the relation R. Good, so this is the basic hash join. The second query I'm going to show you is a cyclic query that lists all the triangles consisting of one edge from R, one from S, and one from T. Again, I'm going to make the assumption that the sizes of the three relations are the same. They have m tuples. Of course, you can compute this in 2 rounds by joining R and S first, and then joining the result with T. But quite amazingly, this query and any full conjunctive query can be computed in 1 round. And if you haven't seen this before, I suppose many of you have seen this algorithm before, but it's a fascinating algorithm. It was introduced in this form by Afrati and Orman in an EDBT paper in 2010. And later they called it the shares algorithm. Now, we analyzed it in a paper in 2013. By then, it didn't have a name, so we called it the hypercube algorithm. So now we have 2 conflicting names, and I'm going to refer to this algorithm as a hypercube algorithm. Okay, so here is the algorithm. It's very cute. So take your P servers and organize them logically in a cube. A cube where the size of the cube is P to the power 1/3. What I mean by this is that every server is uniquely identified by a triple IJK, where each IJK is between 1 and P to the 1/3. For example, if you have 1,000 servers, if you work for one of those companies who can afford 1,000 servers, then the size of the cube is 10. Okay, it's 10 by 10 by 10. Okay, so then what we do, in the single round, in the single communication round, every server that has a fragment of the R relation will compute 2 hash values, one on X and one on Y. And that gives it 2 of the 3 coordinates. We know the I coordinate and the J coordinate in the cube. We do not have the K coordinate, the 3rd coordinate. So what we do there, we simply we send this tuple to this, logically we send it to this face of the cube, but we also replicate it by sending it to all the servers that agree with the I and J coordinate, regardless of their K coordinate. So there is a little bit of replication involved. If you keep in mind the example with 1,000 servers, we need to copy this record 10 times. Okay. In parallel, every server that has an S tuple will compute the hash values for I and actually J and K, and will replicate it along the other dimension. And the same thing for the T tuples. They're being sent to the 3rd phase and replicated there. And here my animation kind of lost its steam. So a beautiful algorithm. We can compute all the triangles in a single communication round. We have to pay a little bit of replication. The replication is essentially the size of the cube, P to the 1/3. In practice, what we observed is that you also need to have a very efficient algorithm that locally computes the triangles, because this is what you need to do after the communication step. The choice of that algorithm is actually critical. But in this talk, I'm not going to focus on what to do once the data is received as a servers. The goal is to just send it to the servers and enable them to compute the query locally. Good. So what is the load per server for this hypercube algorithm that computes all the triangles in one round? And it turns out that the load is quite expectedly m by p to the 2/3. The right way to think about this is that we send each tuple to a face of the cube. And that face has p to the power 2/3 servers. Later we replicated this, but this is secondary. The important thing is that we hashed it into a number of buckets, which is p to the 2/3. But of course, we want better. This is not a linear speedup. We would like to have a load which is m by p. Can we compute it with a load of m by p? And the answer is no. Come on. Any one-round algorithm must have, it's necessary to have a load of m by p to the 2/3, even if the input has no skew. And that is an important emphasis. Sometimes you can prove such lower bounds by exploiting the fact that the output is very large. But as I will show you the proof for this theorem, even if the output is not large, if it's very small, we still need to pay a communication cost which is at least m by p to the 2/3 per server in order to compute correctly all the triangles. So how do we prove such a theorem? How can we prove that it is necessary to communicate a certain amount of data? This is a problem in communication complexity. The results there, however, they tend to I mean, for communication complexity results, if you exchange all the data, that is kind of the naive solution. The bounds are much, much lower. Here, we would like to exchange all the data, and we still cannot get the answer. We need to exchange more than the data. We need to pay some replication. Good. So on the next 9 slides, I'm going to prove this theorem. So if you are not interested in proofs, this is a good time to do some email. But if you like theory, this is a great place to pay attention. This is what I want to prove. Let's try something simple. Let's take a worst case input database without skew and just show that you have to have a load which is m by p to the 2/3 because somehow so much data needs to be communicated. So what is that worst case input database? And if you think about this, I have not restricted in any way how the model can encode information in the messages that are being exchanged during the communication step. So if you have in mind a very, very bad database, a very smart algorithm could actually have a smart encoding that for that database only uses 1 bit. Now, there is 1 bit for each input server. So by just communicating p bits, you have identified that single database. And with a very small load, you can compute the answer because the servers, they will just know this database and will output everything, all the right outputs. Now, of course, with such a smart encoding, you are lost if the database is different because you need to encode those other databases as well. But this shows that there is no worst case database. This proof will not work. We need something smarter. So what we need is an expectation argument. We need to allow the input to range over a larger number of databases. And we are going to choose random permutations over the domain. And this is the only place in the tutorial where I'm going to use the domain. The domain is of size n. And every relation R, S, and T will be a randomly chosen permutation over a domain of size n. What I show there is a relation which is a permutation over a domain of size 4. The permutation, it means that in both columns contain all the numbers from 1 to n exactly once. That's one way to read a permutation. Okay, now it's important to examine the number of bits needed to encode a permutation. Since there are n factorial permutations, we need log of n factorial bits to encode permutations. There are 3 of them, and we want to prove that the lower bound per server measured in bits is at least 3 times log of n factorial by p to the 2/3. This is a notation that I'm going to use for the next few slides, L sub lower. This is the bound that we want to prove that every algorithm needs to pay in order to compute the triangles over all the input random permutations. Notice that random permutations, however you define skew, random permutations are not skewed. Every single value occurs exactly once in the database. Now, the formal statement that we are going to prove is the following. Take any algorithm, and all this algorithm does is that it's guaranteed to return a subset of the query answer, maybe the entire query answer, maybe just a subset. And if this algorithm has a load L, then the expected number of triangles that it can output over all the input permutations RST is only this fraction, L by L lower to the power 3 by 2, of the correct number of expected triangles that the query wants you to return. Okay, this is a formal statement that we are going to prove. Okay, so we will do this in 3 steps. First, I'm going to do a simple exercise. Compute how many triangles do we expect in the output. And then we are going to get to the core of understanding lower bounds in this model, namely reasoning about the number of certain tuples encoded by a message at a server U. And finally, I'm going to show you a very interesting inequality. Again, a time to wake up here because it's a really cool inequality. And then we put them together and we will prove this theorem. Okay, so let's start with a simple exercise. R, S, and T are 3 random independently chosen permutations. Oh, I gave it away. I wanted to ask you, what is the number of expected triangles if we randomly choose 3 permutations R, S, and T? Well, it says here, it's 1. But you know, for people in this room, it's a matter of a simple exercise. For many people, it's a little bit surprising. But if you think about this, if you compute the triangles of 3 permutations, you get at most n triangles, because the resulting table of triangles will have the same property. In every column, every value occurs at most once. Every node can participate in at most one triangle. How do we compute the number of expected triangles? It's a simple exercise. We sum over all possible triangles the probability that that triangle actually occurs in the input, which is the probability that ij is an R, jk is an S, ki is an T. At this point, we use independence, an important step. So we use independence. We can multiply these probabilities. Each of these individual probabilities is 1 by n, and therefore we get n cubed times 1 by n cubed, which is 1. So this is the bar. This is what the algorithm needs to return. It needs to return an expectation, 1 triangle. Okay, now let's see what the algorithm actually learns by receiving these bits about the input. And this is really the kind of the most technical part of this tutorial, when we examine what can we learn from a limited number of bits about an input database. So just to make the notations clear, we have a message consisting of L1 bits about R. We have a second message with L2 bits about S, and the third message of L3 bits about T. And I should have mentioned, I'm focusing on a fixed server. I chose one server, and this server receives these 3 messages that are computed from R, S, and T. And the sum of L1 plus L2 plus L3 is at most L bits. We could assume each of them is L by 3, but it turns out we don't need this. Here is a critical definition. I'm going to talk only about R. The others are similar. Fix a combination of bits, message 1. We define the set of certain tuples encoded by message 1 to be the set of tuples ij with the property that every input, every relation R, every permutation R that encodes into this message contains ij. This is exactly like an uncertain, like an incomplete databases. Message 1, this small number of bits that we learn about the relation R, defines an incomplete database, defines a set of all input permutations that will result in this message being received by our server. Yes? So I'm assuming the question was, do I assume that the algorithm is deterministic? Yes, and thank you for reminding me to make an important point. I'm assuming that the algorithm is deterministic. The statement we are proving is a statement about the expected number of triangles that the algorithm can return over all the input permutations. Since it can't return all of them, there must exist one input on which this algorithm fails. And there is a standard argument due to Yao that shows, converts this into a statement that every randomized algorithm has some input database on which it fails with high probability. Thank you. I wanted to mention this. I'm not going to talk about this in the talk. Please look forward to our paper about it's actually an interesting piece of theory there too. So getting back to this slide, we receive a small number of bits. There are many possible input permutations that encode into these bits. And I'm going to ask a question. I'm going to define the number of certain tuples to be all the tuples that are present in all these permutations that encode in the current bits. Okay, so similarly, K2, case 3 about SNT. So here is the technical lemma, the crux of this proof that will allow us to prove the lower bound. And this says that over the expectations of a single random permutation R, the number of input tuples, the number of certain tuples, the expected number of certain tuples is at most a fraction of the total number of tuples n, and that fraction is the entropy of the message divided by the entropy of the input relation. Now, to remind you, the entropy of the input relation, since we have n factorial permutations, each of them is equally likely. The input of the entropy of the input permutation is exactly log of n factorial, just by definition. The entropy of the message is a little bit more, it takes up some time to visualize it in your head. The probability distribution on the bits of the message is not uniform. We don't know what it is. But what we know is that the length in bits of this message is at most L1. So we have a bound on the size of this message. The lemma says something incredibly boring. It says that if you only receive half of the bits needed to represent R, then you can only be certain about half of its tuples. If you only receive 1/10 of the bits, then you can only be certain about 1/10 of the tuples. Okay, so it's very intuitive, but I think it's useful to actually see the proof. And the proof, of course, uses entropy. I'm going to go a little bit faster. I'm going to make the slides available online. We start with the entropy of R. It's the same as the entropy of R together with the message. The message is computed from R. Now we apply the chain rule. The second line is important. So this is the entropy of the message plus the expected value of the conditional entropy conditioned on a particular bit combination of the message. And the expectation there is over the random permutations R. This is a crux. Once we have frozen this message, a message M1, if we happen to learn many tuples, if we are certain about many tuples in the input relation, there are very few permutations left that have exactly these tuples. And this is the essence of this next inequality. The proof is over here. I'm going to tell you the highlight. I'm not going to discuss the details. Once we know that this message has so many certain tuples, the resulting entropy is at most log of n minus the number of certain tuples factorial. So massaging brings us back to log of n factorial, which is the entropy of R. And this gives us this inequality that connects the entropy of, that connects the entropy of the message with the expected number of certain tuples. So now we have in a single line the entropy of the message and the expected number of certain tuples. And from here on, it's just manipulation, and we get our result. The expected number of certain tuples is at most the fraction of the ratio of the entropies of the message and the entropy of the input relation. Again, it's a boring statement, but it is a rigorous way to make an intuitive claim formal. It's also a general principle how you can prove this. For permutations, the derivation is very elegant. If you apply to different probability spaces, you need to go again through these calculations, and it might vary a little bit, but the technique is it's quite universal. It spans beyond this. Yes?
I realize that the inequality is this is make it equal. Is there a message for inequality?
Right. Is there a message for which this is inequality? Good question. Is there? Can we design a message for this is inequality? Yes, hash-based partition, hash-based partitioning, which means that we take our permutation, we divide the domain on one column into p fragments, and the message encodes one of these p fragments, and then this works out. There might be small constants there that are you need to add or subtract, but yeah, so we can realize equality. Good. So now we're moving towards the third step. We are going to put this together, but now I'm going to make a detour and show you a fascinating inequality that probably very few people have seen. A brief background, the fractional edge cover of a hypergraph. So a hypergraph is, of course, a pair, a set of nodes, and a set of hyperedges. It is standard in database theory to associate a hypergraph to any full conjunctive queries without self-joins. So at the top, I have a full conjunctive query without self-joins. These relations S are distinct. And I'm going to think about this as a hypergraph with the nodes being the variables and the edges are the atoms. A fractional edge cover of the hypergraph consists of one non-negative number associated to each hyperedge, such that for every variable, for every node, the sum of the numbers associated to the edges incident to that variable is at least 1. The dual notion is that of a fractional vertex packing, associates numbers to vertices, and the sum for each hyperedge, the sum of the weights of the nodes in that hyperedge is at most 1. And by duality, the minimum value of a, what did I write here? I wrote wrong. It should be the maximum value of the vertex packing is equal to the minimum value of the fractional edge cover, and this is denoted with rho star, which is also called the fractional edge covering number of the hypergraph. This is the same rho star as in the AGM bound. If people are familiar with the AGM bound, I'm going to review it later in the tutorial. It's a very well-known bound in that recently has kind of impacted the database theory community. Okay, so this is my background. For example, I have two examples here. The second one is more interesting. For the triangle query, a fractional edge cover places 1/2 on each edge, which is better than placing 1 and 1, which would correspond to an integral edge cover. Good. Here is a really cool inequality, was introduced by Friedgut in a paper in 2004. And it says the following. It's a little bit dry, but it's going to become very nice in a few seconds. For any hypergraph, fix a hypergraph. For every edge, for every hyperedge, associate a sequence of numbers. So A1 indexed by x1 is a sequence of numbers for each set of indices in n. I should point actually here. So A1 indexed by x1 is a set of non-negative real numbers associated to every x1 tuple in the domain. And then what this inequality says is that the sum of the products of those sequences is less than the product of the sums to the right powers. Sounds dry. Here is an inequality that you know. We apply Friedgut inequality to an intersection query. So this query intersects R and S. The corresponding hypergraph has one node and two hyperedges containing that node. The fractional edge cover that I'm going to choose is 1/2. A sequence associated to R is AX for each x in n. A sequence associated to SX is BX. And then Friedgut's inequality becomes Cauchy-Schwarz. What does it become if we have three terms here, Rx, Sx, and Tx, and we cover them with, I don't know, 1/3, or any three numbers whose sum is greater than or equal to 1? Any hints? Then it becomes the generalized Hölder inequality. So I didn't put that on the slide, but here I put a different inequality. So we can apply the same principle to the triangle query. And then we get this amazing inequality that the sum of all AXYs times the BYZs times the CZX is less than the product of their sums to the appropriate powers. I find this interesting. So by now, we think that we have seen all the elementary inequalities. We know the Cauchy-Schwarz, we know the Hölders, we know all the Jensen's inequality. And then you see this. And it's completely new. It kind of blows you away. I mean, it blew me away. And it's more than this. You can construct such an inequality for any hypergraph and for any fractional edge cover of that hypergraph. Quite cool. Good. So finally, we have all the ingredients and we can put them together to prove our upper bound. So the formal statement, the lemma that we need, which essentially almost brings us to the theorem, is that for any fixed server, the expected number of triangles that that server can report is at most the load that we allow that server to have, divided by 3 log n and factorial to the power 3/2. So how do we do this? Well, we are going to examine the probability that this server knows an edge ij, and similarly that the server knows jk and ki. This probability is at most 1/n, because to know the edge ij, the edge must be present, and moreover, the message must encode the fact that it is certain. But it can be in general less than 1/n. Good. So let's compute the expected number of triangles that the server can report. I'm going to assume independence as before. This is a critical step. So it is a sum of the products of these 3 probabilities over all the potential triangles. Now we are going to use Friedgut inequality. This is a beautiful place where we use Friedgut inequality. Now we need to compute the sum of these probabilities squared. And this is where we use the fact that we know the sum of the probabilities. The sum of the probabilities is the expected number of known tuples. But we need the sum of the squared. For that, we are going to use also the fact that aij is at most 1 by n. It's no larger than the probability of ij being in the input relation. This brings us to this inequality here. We have a product of L1, L2, L3. We apply the arithmetic geometric inequality to get the sum. And this is exactly the inequality that we stated in the lemma. And from here, we obtain the theorem. The entire algorithm has only p servers. So the total number of, the expected number of triangles that the algorithm can return over all these p servers is only p times larger. And some massaging gives us exactly the bound in the theorem. Good. So that was my long and boring proof. Now you can stop reading email, because now I'm going to show you how this extends to general queries. So far, we only discussed joints and triangles, and we understood that these are the optimal bounds for computing joints and triangles. Let's see what the optimal bound is for arbitrary full conjunctive queries. So the full conjunctive query looks like this. It is a conjunction of L atoms, S1 up to SL. And to compute it in one round, we are going to use the algorithm introduced by Afrati and Ullman, which we call the hypercube algorithm. We are going to write the number of servers as a product of k numbers, one for each variable. And we will call these factors shares. And then the algorithm in a single round will send every record of some relation Sj to all the servers whose coordinates agree with the hash functions applied to these existing attributes, and will broadcast along the dimensions that are missing from this tuple. And after this single communication round, we will compute Q locally. This is exactly the triangle algorithm generalized in the obvious way. The interesting theoretical problem is what is the optimal choice of these shares that minimizes the load? And the load, I'm going to replace a sum with a max here. So I'm going to compute the load due to Sj, and this quantity is m divided by the number of buckets that we use to partition Sj, which is the product of pi's for all the variables in Sj. And instead of sum, I'm going to use max. And this is a loss of a constant of at most L. Since we use max, this can be actually optimized by applying logarithm. I'm going to show you directly the answer, but I still need a short detour into another definition of a fractional edge packing on the fractional vertex cover of a hypergraph, which is like the definition before, but with inequalities inverted. So the fractional edge packing insists that the sum of the values of associated to the edges incident to any given node is at most 1. And for the fractional vertex cover, we want them to cover every edge. Their value should be at least 1. Here it is a correct min and max. So the minimum over fractional vertex cover is the same as the maximum of fractional edge packings. This quantity is denoted tau star. No connection to the AGM bound. This is not rho star. Sometimes it's smaller, sometimes it's bigger than rho star. I have more to say about this. Bas Ketzmann will have much more to say about this in the evening. But right now, just let's agree that they are unrelated. So here is what the load of the hypercube algorithm is on a general conjunctive query. It is exactly m by p to the power 1 by tau star, 1 by the fractional vertex covering number of the query hypergraph. Interestingly, the corresponding shares can be obtained by taking an optimal solution of the vertex covering of the fractional vertex cover and raising p to the power that fractional vertex cover divided by tau star. And the lower bound is that any one-round algorithm requires this load. There is no better algorithm. So it means that we know how to optimally solve any conjunctive query in one round. To give you a quick sense, this is a hypergraph of a join. How do we cover both edges the cheapest way? Well, we place all the weight on this node, and this covers both edges, which means that in a join, we want to hash partition on the join variable. Okay. Here is a triangle. Here we cover it by placing 1/2 on each node, which means that the shares will be p to the power 1, 2 divided by 3 by 2. And finally, if we have a longer chain of joins, then the optimal fractional vertex cover will place 1 and 1 on these two nodes. And what this tells us is that we want to hash partition based on these two nodes in parallel, and then compute a Cartesian product. Okay, any questions about this part?
Or when the relation sizes are the same, right?
This holds only when the relation sizes are the same. Very good. So this summarizes the case. When we have one round, no skew, and all relation sizes are the same. Now people look at the clock. Are we ever going to have lunch? But the rest it's going to be increasingly faster. So just to summarize, the optimal load here is given by the fractional edge packing, fractional vertex cover of the query hypergraph. And that is the takeaway from this part of the talk. So Semik has the right question. This only happens where the relations are equal. What happens if they are not equal? How do these formula changes? So let's talk about unequal inputs. Unequal inputs, I mean, knowing the size of the input tables is the simplest statistics that any database system has and exploits. The state of the art is that basically every database system makes some decisions based on the sizes of these relations. For example, and this is again something that all systems I've seen do, if you were to compute a join and the relation of R is much smaller than that of S, then you want to broadcast R and not to partition it. Just keep S unchanged. So the question is, how does this optimal load changes now as a function of these unequal inputs? Okay, and I'm going to start with an intuition, which is very simple. There is a little bit more, too much math there, but you can ignore it. The intuition is super simple. And the intuition is given by this observation that if we want to compute the cross product of two relations R and S of sizes potentially unequal, M1 and M2, then the optimal load is a square root of M1 M2 by P. It's actually times 2, but I'm ignoring constants. So to see this, the natural thing to do is to think about the algorithm. How can we compute the cross product in one round on P servers? Well, you organize these P servers in a matrix. It's a hypercube algorithm. You organize these P servers in a matrix. We don't know how big the dimension should be, P1 and P2. And then we hash partition R to the rows, and every record R is going to be replicated across the entire row. And we hash partition S to the columns, and we're going to replicate S to the entire column. And after this single communication round, every server will output locally all the tuples that it has received. It's easy to optimize for P1 and P2, and we get that the load is indeed what we have there. It's also quite easy to prove the converse. Any algorithm requires this load. And you can prove this by reasoning about how many tuples it receives from R, how many tuples it receives from S. It can output at most their product, which is less than their sum by 2 to the power 1/2. So it can output at most square root of L by 2 tuples, where L is the load that you have allowed for that server. Multiplies it with P servers, and we get our bound. Good. A very simple formula. And it's very easy to prove. You can do this, on the back of the envelope, and proves that this is the optimal load for computing the cross product of two relations. As a side note, notice that if M2 is much bigger than M1, then you want to have this matrix very long and short. I mean, what am I saying? Very wide and very opposite of tall, very short. At an extreme, we will have P2 equals to P and P1 just 1. That corresponds to broadcasting R to all the servers. So broadcast is a special case when this matrix degenerates to a vector. Okay, what happens if we want to compute the Cartesian product of C relations? By now you know it. Just generalize. It's like if we know how to do it for 2, we know how to do it for anything. So it is this simple formula, the product of their sizes by P to the power 1 by C. Now comes a very simple insight about a general query. Take any conjunctive query, full conjunctive query, doesn't have to be a cross product. The input sizes are M1, M2, and so on. A packing of the conjunctive query is defined as a subset of atoms that do not share any variable. This is exactly an integral edge packing. So a subset of atoms, they don't share any variable. So any one-round algorithm that computes correctly this query must have a load at least equal to the load given by computing the cross product of the atoms in this packing. It's very easy to see why. Because you only have one round. The one round here is really critical. You only have one round. So the servers that hold the values in the atoms and the relations given in this packing, they don't know about the other relations. So unless they send the tuples such that all the tuples in the cross product of these relations sits on one server, unless they do this, you can modify the other input relations to ensure that this tuple will actually participate in an output. And then the algorithm is not going to be able to report that output. Good. So for any packing, the algorithm must have a load that is given by this, at least a load that's given by this formula. So yes.
Simple join, R, X, Y, S, Y, C. You have sharing, right?
Right. So if we have a single.
So in that case, what is the saying?
Yeah, good.
It's trivial, right?
Yeah, it's a trivial statement. Let me say it in the microphone so people can hear it. So the question is, what happens if the query is a join? So if I have a join, we have just two relations. They share a variable. So in that case, a packing can only contain one of these two relations. And this observation says something trivial. So C is 1. So it says that the load is at least M1 by P. And it's also at least M2 by P. So it is at least a maximum of M1 by P and M2 by P. That's where I'm heading. Okay, so this is now the theorem that completely characterizes a load for computing a conjunctive query with arbitrary input sizes in one round. For any fractional edge packing, not just an integral one, for any fractional edge packing, define this expression. It is a geometric mean of the sizes with the weights given by the fractional edge packing divided by P to the power 1 by the value of the fractional edge packing. For any such choice, this quantity is a lower bound on any one-round algorithm computing that query. It follows that the maximum overall fractional edge packings is also a lower bound. And it turns out that that maximum is actually also an upper bound. We can find matching shares for the hypercube algorithm that achieve exactly this load given by the maximum of LU over all possible fractional edge packings. Very interesting. The thing to take away from here is a maximum. This is what database systems do. They analyze these sizes and they choose one query plan or another query plan. And this is a mathematical formulation of choosing one or another. So let me show you how this works for triangles. So in the case of triangles, there are only 5 possible fractional edge packings. Of course, there are infinitely many. But what I mean is that the fractional edge packing polytope has only 5 vertices. Everything else is a convex combination of these 5. So how can we pack the edges? We can place 1/2 on each edge, or we can place 1 on this edge, and then we are stuck with 0 on the other 2 edges. Similarly with 0, 1, 0, and so on. Or we can place 0 everywhere. Here is what the theorem tells us to do. It tells us to compute this formula for each of these fractional edge packings, which I did. And as you can see here, we get some trivial lower bounds. Of course, a load is going to be at least the size of R divided by P. This is a super trivial lower bound. We need to take some maximum of all these lower bounds. And that maximum is the correct bound of the query. We need to decide which one is the maximum one. The 0 is never the maximum one. If the sizes are about the same, then this will be the optimal. And then the shares of the hypercube algorithm are given by some primal linear program that I didn't show. The second case is interesting. This is when this happens. This is a maximum when MR is much bigger than the other 2, and the exact relationship is this one here. So this corresponds to an algorithm that, as you can recognize, will compute the cross product of S and T, ignoring Z. It's like setting the exponent of Z to 0, which is the same thing as this share is 1. It's going to ignore Z. So it's going to compute the cross product of S and T, while R, which is a big one, is going to partition both on X and on Y. And it's going to be uniformly partitioned across the matrix. Okay, notice that such an algorithm takes advantage of the fact that some relations are much smaller than the others, and it can improve the speed up from P to the 2/3. It can improve the speed up to just P. It's actually also interesting to notice, I only want to show you, point you to this graph. I'm going to make the slides available online. This graph shows you that as P increases, you are forced to move this, vertex of the fractional edge packing polytope. You're going to move it closer and closer to the optimal, which essentially is bad because you're forced to reduce the speed up from something that's possibly good to 1 by P to the 1 by tau star, which is kind of the slowest speed up you can expect for that query. Good. So to summarize this part, what we have here, the takeaway is that when the sizes are unequal, your formula is a max. Is a max that depends on which sizes, how unequal these sizes are. That's a high-level takeaway. And sometimes this load can be better than assuming that all the sizes are equal because we might get a better speed up. Good. So I have like, how many? Oh, 12? Oh, I'm in good shape. So 12 minutes is good. I thought 2. Yes.
So when you said as P increases, you have to get closer and closer to the optimal. What do you mean by the optimal?
Yeah, let me.
Meaning when the sizes are the same.
Exactly.
So your first row in the table.
Yeah, yes, the first row in the table. One way to think about this is that if the sizes are unequal and you only have a few servers, these servers, they will take a big load. So the smaller relations, they are negligible. You can broadcast them. As you increase the number of servers, you expect a better and better load per server. So now your small relations are no longer small. They don't look small anymore. You need to account for them when you do the partitioning, and you lose the advantage of small relations. That's the essence of that graph. And I think it explains beautifully what happens in practice. That's exactly what happens. As you increase the number of servers, you observe such. It's much harder to parallelize as you increase the number of servers. Good. So the takeaway here is that expect to see a formula that has max, that tells you to choose between the various optimal values. So far, everything we discussed was assuming that there is no skew in the data. What happens if we have skew? Well, skew completely ruins everything we discussed so far. Skew is a very serious problem in shared nothing in general in databases, but especially in shared nothing architectures. It degrades performance significantly. My experience with one particular large-scale data analytics system is that they do nothing. Okay, so if you have skew in the data, it's amazing. You compute these 5-way joins on a ridiculously large number of servers, and the answer comes back in 2 seconds. And you go, wow, it's fascinating. You make a small change, and then it runs for half an hour, and then it crashes. It doesn't return anything. What happens is that because of skew, the internal memory is exceeded, and it also because of skew, it took forever. The internal memory is exceeded, and the system just crashes because it doesn't know how to cope with skew. So understanding skew and coping with it is very important, is a critical challenge. And here the takeaway that I'd like you to take away is that you need to treat heavy hitters differently, and you need to treat them with a different query. Still a query that we already understand, it's just a different query. It's a residual query. So let's see this with a join. The standard way to handle a join is to hash partition them. So we think about the P servers as being an array. Of course, this only works if every data value y occurs at most m by p times. Otherwise, if it occurs more than m by p times, then one of these servers will be overloaded. What happens if it occurs more than m by p times? What happens if there is a single value y? Then we don't compute a join. Let's face it. Then we don't compute a join. Then we compute a Cartesian product. And we know how to compute a Cartesian product. It's a different algorithm. It's not the same. It's an if-then statement. We compute it by organizing the servers in a matrix. And now we are forced to pay a higher load. It's a slower speed up, and it is a higher load. So that's how to think about skew. And this can be made precise, which is what we did in an ICDT paper. I'm going to share you the details. They are rigorous. I don't find them super enlightening, except with this take-home lesson that you need to reason by cases. You need to treat separately the heavy hitters from the light hitters. I have here an example using the triangle queries. The way to compute it is to identify all the heavy hitter values, and there are at most every heavy hitter occurs at least m by p times, so they can be at most p of them. A small number. Remember, the data is terabytes, p is a few thousands. And then you run several queries in parallel, depending on which values x, y, z are heavy or light. If all of them are light, then you run this query, the standard triangle query, with a load of m by p to the 2/3. In parallel, you identify all the z heavy hitters, and then you just ignore them. And if you ignore them, you run a different query. And that has, by necessity, a higher load. And in parallel, you run other queries, and so on. And the biggest load is here. Sorry, this one here. And this turns out to be your overall load for computing this query on an arbitrary input database, not just on a skew-free database. OK, so the takeaway here is that once we have skew in the data, it is necessary to accept a higher load. Theoretically, the load has to increase, and there is nothing we can do about this. Okay, so far we have considered only one round. What happens if we run in multiple rounds? Just to make sure, in case I need to stop early, this is a topic that Bas Ketzmann will cover in his talk in the afternoon. Of course, we want to understand and analyze the hopefully lower complexity when you allow more than one round. It turns out that the theory here is much more difficult. But what I hope to show you now is a very simple lower bound. A lower bound on the load that is very simple to understand. And this brings me to the AGM bound. How many people in the room already knew the AGM bound? Just a show of hands. Okay, I think it's a fantastic result due to Aterias, Krohe, and Marx. And it really explains a lot in database theory. And it says this: for any input database where all the input relations have size at most m, the size of the query is no larger than m to the power rho star. And rho star is a fractional edge covering number of the hypergraph. And they have a dual. They say that there exists one database, which is a worst database for which all the input relations have size at most m, and the size of the query is exactly m by m to the power of star. Exactly means asymptotical, exactly. The proof that they give uses entropy, but I advise you to retrace a proof using Friedkreuz inequality. It's so simple. The values Aij that you need in, oops, what did I do here? The values Aij that you need in Friedkreuz inequality, they are exactly the indicator variables, 0 or 1, depending on whether the value Ij is in the relation or not. Then Friedkreuz inequality gives you exactly the AGM bound. The worst case database is a very skewed database where every relation is a complete partite graph. In this case, every relation would be a complete bipartite graph, a very skewed database. This result helps us prove a very simple and intuitive upper bound, a lower bound, I should say, on the load on any algorithm that computes a query in any number of rounds. And the load goes like this. Let me actually give you the proof, and it's informal. Start with that worst case database. And we know that the number of output tuples is m to the power of star. After a number of rounds, what can the server learn? Well, some subset of each relation Sj that is at most r, the number of rounds, times the load, the number of tuples it can receive in each round. By the AGM bound, this server can output at most this new m, r times l, to the power of star. So together, all these p servers can output at most p so many. And this has to be at least m to the rho star, because that's the size, that's the required size of the output. Do some maneuvering, and we get this bound here for the load. Now, at this point, unless you were hungry, you would probably object. There is no worst case database. Okay, this is what I argued. But from here on, it's not that hard to figure it out. We don't consider it a single worst case database. We consider sufficiently many whose output is sufficiently close to that. And the math gets a little bit more messy, but it's doable. So this is actually fascinating. So we don't know what the real answer is, and Bas will have a partial answer. For one round, this load given by tau star holds here, even if the database has no skew. And it's a load that is proven without exploiting a large size of the output. It is inherent in the communication cost that we need to pay to answer the query. For many rounds, we only have this other bound, which is derived from using an input database where the output is huge. And this gives us a very general bound. Bas Ketzmann will discuss the case of graphs in the afternoon. And in that case, one can prove that tau star is less than rho star. And he will show that the second one is a true bound for graph databases. For cycles, for example, these two bounds happen to coincide, so then the one round and the many rounds is the same. But for general hypergraphs, there is no relationship, and this is going to be the open. This is an open problem. Okay, so let me just summarize the multi-round. So what happens here is that we can recover some of the extra costs that we paid for skew. We can recover for some queries, like the triangle queries. This is a fascinating algorithm that I didn't describe, but Mas will describe it in the afternoon. But beyond that, it's pretty much open. It's pretty much open what the optimal cost is as a function of the number of rounds. Good. So I think I should stop here. Just to review, we discussed basic query processing. We discussed there how to use entropy to prove lower bounds on the load. The takeaway is that the load for non-skewed databases is given by the fractional edge covering number. Once we move to non-uniform cardinalities, the algorithm hopefully can take advantage of the smaller relations and improve the load. There, the takeaway is that the load has to be a max over the various possible query plans. Skew necessarily increases the load. We have no choice. We have to pay a higher cost, and the way to deal with skew is to use residual queries to adjust to the heavy or light hitters. Multiple rounds is pretty much open. Many of my open problems have to deal with multiple rounds. Here we have a different lower bound based on the fractional edge covering number, but that holds for databases with skew, so it's completely different. So I will stop here and take questions.
Great. So because it's lunchtime, I think it's okay to take a couple of questions. We're right on time, so there's one question here.
So you mentioned that the worst case instance for the AGM bound has skews. I thought that has no skew. The worst. Yeah. So,
yes. So hunger pays too much attention. It's true. According to the way I define skew, the worst case instance for the triangle query is actually not skewed. So two answers here. One is that for some query graphs, if the value of the fractional edge packing, vertex packing is 0, then you get a single node in the worst case instance, and that gives you a totally skewed value there. But that is not a satisfactory answer. Actually, I don't have a satisfactory answer. I only have the observation that for the worst case instance, the output is huge, while the lower bounds that we proved for the one round, they are for instances where the output is very small, and I see there a tension.
Yeah, I just wonder what the state of the art is on queries that are graph path queries. So now you have one of those, right? So R of Y. So you follow and say, can I follow the path of length 3 or something like that in this graph? So what is the state of the art in terms of parallel execution on such objects?
So path queries, where we have a joins that form a path. So the question is, what is the state of the art for parallel execution of conjunctive queries whose hypergraph is a path? So they fall completely under what Bas Ketzmann is going to cover in the afternoon, and he's going to look at the case when the data is skewed, and you use multiple rounds, especially to deal with the skewed values. So this is one way to look at this. The other way is how can you optimally compute these queries, assuming that the inputs are permutations? So it's a theoretical problem because real databases are not permutations. But in that case, you can actually improve the lower bound will be much lower than what Bas is going to present. And I think we kind of understand there what the optimal cost is, but we don't understand it beyond very simple path queries. how to improve the load even for permutations.
So thanks for the nice talk. So I have a question about the hash functions. So you're just using any kind of hash function, selected from like a family of universal, you know, but is there something more to say there, like from a practical perspective, or it doesn't really matter, like, you know, what kind of hash functions are being used?
There is a lot to say, but I'm afraid people want to have lunch. So the analysis that the hash partition that we're using in the hypercube algorithm is non-standard. We don't throw balls into bins in the standard way, but you use these two or multiple hash functions to decide on the bucket. This is a non-standard analysis that required a new investigation of the distribution, and it's going to be included in our upcoming journal paper. In terms of practical use of hash functions, you need, what I tell my students is never write your own hash function, because you're going to get it wrong. It's going to have a bad case. You want to use a professionally written, and the best way to do it is you combine it with a salt, with a random seed that you use the entire day or the entire month or something like this, and you vary that random seed, so you have some randomness in your hash function. So even if one day your query runs very slow and you wonder why, it's going to be a very rare event, because of the random choices of that seed, your queries will run in the right time.
Okay, let's thank Dan again and proceed to the lunch. Thank you very much for coming.